So far in the last lecture, we saw what condition gave rise to the circular orbits, the elliptical orbits, the parabolic orbits, and hyperbolic orbits. Now, we are going to continue our discussion through that. Now, in this lecture, I'm going to introduce you to what's called as the energy diagram. Energy diagram. The effective potential term, we are going to define a quantity called effective potential energy, and then we are going to see the orbits descriptions in details. Alright, so first details. So first we are going to see let me define what it meant by effective potential. So you need to understand that the energy of a single body, moving in the two dimension can be reinterpreted as the energy of a single body. See, this is single body moving in one dimension, the radial equation. Alright, so our key is the radial equation. So in an effective potential energy, we can define a quantity called effective potential energy. Now we can define a quantity called effective potential energy, which is defined as L square upon 2 mu r square minus G m1 m2 upon r. Now, how this is different from our current potential energy is quite just we have this additional term. So I can define the total energy E, which is equal to K effective, which is the effective kinetic energy, plus the U effective. What is my K effective then? It's half, rather than m velocity square, it's mu r dot square. Mu is the mass of the two-dimensional energy in a single body moving in two dimension, which is interpreted in a single body, right? That is basically the definition of the reduced mass. So U effective is a function of r by r naught, right? So if, let me take a situation, if K effective, if I set K effective to be equal to 0, then from this equation I know my energy, my total mechanical energy will be equal to this effective potential, right? I know what is I know my effective potential term, which is given by this particular equation, L square upon 2 mu r square minus G m1 m2 upon r. Now that's great. This is my total mechanical energy, which is equal to my U effective, and my U effective is now defined by this, which is also equal to the total mechanical energy. Now, if you know from the definition of potential energy, we can define a force. I mean, it's actually the potential energy. The difference. I wanted to make sure you understand this. I wanted to convey this message for a long time. See, potential as a whole is meaningless. It doesn't make any sense. But when we take potential difference, or say the potential energy difference, it makes an astronomical difference. See, that's what's important in electrostatics, right? When we in electrostatics, you define the potential as a function of r, where you say the r is blah blah this, we have this kind of situation, and then we define a force, we define an integral where we take this, where we take this symbol is kind of an O symbol, but it stands for the reference point. That's electrostatics. We are not concerned with that currently, but we are going to use the same kind of representation to our ongoing discussion. So similarly, I define a potential effective potential energy difference between say 2 points, say B and A. So B being the higher and the effective at A. See, minus sign defines nothing, but it's kind of a definition. So this whole equation is just the definition of how you represent a potential energy and force relation. So okay, it's cool. Okay. I have to get rid of vector. Do is just take the radial component because that's what is viable to my current situation. Okay, I have this equation. Now we are going to use a very powerful theorem from real analysis. So by, or say from calculus, by fundamental theorem of calculus, or most popularly known as FTC, we get U effective at P minus U effective at point A is equal to the integral from A to B, which is nothing but the partial differential equation of U with respect to R dr. Thus, we define a quantity F vector effective is equal to minus du effective upon dr. This is my force and effective potential energy relation with a negative sign and a derivative with respect to r. Now this is a very important equation to speak. So the U effective describes, what does U effective do? It describes the potential energy required for a reduced body moving in one dimension, as I showed you over here. Okay, this is the reduced system. So what U effective does is it describes the potential energy required for a reduced body moving in one dimension. Thus, I can now get my effective force using this equation, and since we are using a very special case where the potential depends only on r, we can turn this partial derivative into a whole derivative. Again, it doesn't make much of a difference here, but to be intact, mathematically correct, you need to stay in the domain itself. So I'm just using the equation that we wrote. So I just use this equation. This is the equation, right? This is the equation. This equation over here. But basically, my effective potential energy is nothing but the combination of two forces, Fr of centrifugal force plus Fr gravity. Thus, I get an equation L square upon mu r cube minus G m1 m2 upon r square. Thus, in order to write it, let me rewrite it. L square upon mu r cube minus G m1 m2 upon r square. Thus, in order to write it, let me rewrite it. Let me rewrite it. g m1 m2 upon r square. In this sense, this is my centrifugal term. It's a centrifugal, alright? It's a centrifugal, not centripetal. And this is my gravity. Alright. This gives a beautiful description. Now, we are done with the effective potential energy. I want to show you the energy diagram which I have made earlier. So in order to save some time, so this is what the energy diagram looks like. Here on this particular axis, we have U effective, and it ranges from -1 to 1. 2 is just the upper limit that I have used, and 0 is, and from 0 there goes a horizontal axis which corresponds to the U part, and I have missed to write it. U part, which characterized 1 over R2, nothing more. It's not rocket science, and rocket science are easy, it's just as compared to physics, so rocket science can suck it off. So this particular curve here, it shows a rapid decrement as compared to this. You see this increment over here, this is a negative axis and this is a positive axis. It shows a more rapid decrement as compared to this one. But here we have a dip. When we study graph, we more or less use this term like say graph takes a dip, or there is a kink. The kink graph usually goes like this. This is the kink part. It's a kink, and there is this is a Gaussian. It doesn't look like Gaussian, but yeah, something. Now it takes a dip over here at r is equal to r naught, which is equal at minus 1. So this is how you study a graph. You see each of the components. You see that there is you compare with its fellow graphs, fellow lines, or fellow curves for that matter, and you study the indifferences between them, so that you can have a graphical understanding of what is happening. And you see, the graphical understanding provides a more kind of an observational databases. I don't know how to say it, but this is how you interpret graph, and why you need to interpret graph is completely nice, because you want to see something not just in paper but in actual observation. So that's one of the reasons why we study graphs. So this is all about the energy diagram, so as to speak. Now we're going to move to the orbitals, the characteristics of orbitals. So I probably take this on the next lecture, because I have to define the circular orbit, the elliptical orbit, the parabolic orbit, and the hyperbolic orbit. I think it will take some time. I don't want to make the video longer. As I'm speaking, the video is getting longer, so it's not wasting time anymore.